Welcome Algebra 1 students. This is Chapter 8, Lesson 2 in Jacob's Elementary Algebra, and I'm going to go over the lesson and then go through the homework exercises, set 3, to demonstrate how everything works. So in the last video, I went over Lesson 1 and we talked about a number of things, including scientific notation. The idea behind scientific notation is that you're writing numbers as some number, which even if it's a decimal number, it's going to start with a number that is less than 10 and at least 1. And then you're going to multiply it by 10 to a certain power. So, and that certain power, b, is going to be an integer. So whole numbers like 0, 1, 2, 3, 4, and their opposites, -1, -2, -3, -4, will be the types of numbers that can be your integer, your exponent b. So first, some terms for your math dictionary. When I have a number like 10 that's being multiplied by itself, raised to a certain power, this is the base, and then b would be the exponent. So if I have, for example, 30 squared, what's the base? And what's the exponent? The base is going to be 30, and the exponent is going to be 2. All right, so base and exponent. It turns out that you can actually do multiplication with numbers that are in scientific notation in some very useful ways. Like, let's say that I have a number like 2 squared times 2 cubed. So 2 squared times 2 cubed. There's a few ways I could solve that. Method number 1, I'll just say A, would be what's 2 squared? 4 times what's 2 cubed? 8. It's going to equal 32. But if I have really large numbers, then, you know, I might have to do a lot of mental math. If it was like 2 to the 50th times 2 to the 342nd, that would be pretty hard to do without a calculator. And even with a calculator, the numbers would be too large to be able to represent on your calculator screen. But for small numbers like this, this works. I could just multiply it out like that. But let's try another approach. I could say 2 squared, what is that? That's 2 times 2, right? Times, what's 2 cubed? That'll be 2 times 2 times 2. I don't really need that. So that's the same thing as saying 2 times itself 1, 2, 3, 4, 5. So it's actually the same as 2 to the power of 5. So if I were to multiply 2 squared times 2 cubed, it's the same as 2 to the power of 5. Now, I could come to this exponent, the power of 5, a different way. Because when I wrote it out, what was I doing? I was just adding the number of times I'm multiplying by 2, and that becomes my exponent, right? With the base of 2. But could I not have done this? The power of 2 plus the power of 3 becomes the power of 5. So as long as your base is the same when you're multiplying two exponents, then you can just add the powers, add the exponents. So in another example, this black marker's having trouble erasing, so I'll switch back to the purple. We could take something like this. X to the power of 6 times x to the power of 1. Now I could figure this out the old-fashioned way and say x to the power of 6, which is x times x times x times x times x times x. 1, 2, 3, 4, 5, 6. That's really tedious, and I might make a mistake by counting the wrong number of x's, especially if they were like x to the power of 150, and it would take forever if it was something like that, times another x, because x to the power of 1 is just 1x. So how many times am I multiplying x by itself? 1, 2, 3, 4, 5, 6, 7. So that's the same as x to the power of 7. I could have saved myself all that trouble if instead I had thought to myself, all right, do these both have the same base of x? Yes, they do. Can I add their powers then? Yes. So 6 plus 1, x to the power of 6 times x to the power of 1 is x to the power of 7. So this is actually what we call the first law of exponents. So I'll put it here. You can enter this into your math dictionary. First law of exponents. And what that says is if a and b are positive integers, then in other words, when multiplying x with a certain power times x with another power, since the bases are the same, if those integers are positive for a and b, if those powers are positive, I can just add them, a plus b, x to the power of a plus b. All right, so hopefully you wrote that down. The first law of exponents is x to the power of a times x to the power of b equals x to the power of a plus b. So let's do another example. We have 4 times 10 to the power of 4. Is this in scientific notation? Yes. We have an a, which is 4, times a base of 10 with a power or exponent of 4. And these follow the rules for a and for b. So I got that one times 7 times 10 to the 7th. So I'm going to multiply these together. And if I wanted to, I could put parentheses around 4 times 10 to the 4th and 7 times 10 to the 7th, but it doesn't really matter. So what do I do with this? It could be kind of irritating because what I would do if I were to do one at a time is I would say, okay, 4 times 10 to the power of 4. So that's a 4 with 4 zeros. After in times 7, and then 7 zeros at the end of the 7. It could get kind of messy because there's so many digits to account for, but here's the easy way. When I'm multiplying numbers that are in scientific notation, I can remember the first law of exponents, which says that if I've got the same base, I can add the powers. And so now I'm going to take these two and combine them, and then combine the 4 and the 7 separately. You may remember there was something called the commutative property of multiplication, which says that if you've got any numbers that you're multiplying, like here's 4 different terms, 4, 10 to the power 4th, 7, 10 to the power 7. I can multiply these together in any order, and it doesn't matter. The answer will be the same no matter what. So could I actually say I'm going to multiply these two with the base of 10 and the exponents before I multiply anything else or separately from them? Yes, absolutely. So I'm going to do it this way. 4 times 7 times 10 to the power of 4. And I'm actually going to add the power of 7 there. Or if you wanted me to write it differently, like that. All right, so what's 4 to the 4 times 7? 28. And then what's 10 to the power of 4 times 10 to the power of 7? That's, 10 to the power of 4 plus 7. So continuing this over here, what I have now is 28 times 10 to the power of 4 plus 7 is 11. Is this in scientific notation? Almost, but not quite, because remember that in scientific notation A, it has to be a number that's at least 1 but smaller than 10, or in other words, you have your first non-zero decimal, or your first non-zero digit to the left of a decimal space. So I'm going to just insert a decimal here, 2.8 times 10, and it was to the power of 11, but now I've just had to divide it by 8 in order to make it from 28, divide it by 10, in order to take it from 28 to move the decimal over to 2.8. So I have to make up for it by, adding another power of 10. So now 28 times 10 to the power of 11, that's going to equal 2.8 times 10 to the power of 12. So this is my answer. All right, so that's how you multiply numbers that are in scientific notation using the first law of exponents, which says that if your exponents, if you have a number where there's the same base, then you could just add the exponents, add the powers when you multiply those numbers. Okay, let's do the problem set. We're going to go to set 3 and do some problems from set 3. All right, so number 11, it says the product of x times x times x times x times x times y can be written in exponential form as, well, let's see if you can figure this out. How would you rewrite this? X to the power of 1, 2, 3, 4, 5. Because it's x times itself 5 times. Times y to the power of 1, 2. It's times itself twice. So there, I've written this out in exponential form. Now write the following products in exponential form. I'm not going to do too many of these because they take a long time to write, but I'll just do one more. All right, so letter E is x times y times y times x times y times y. If I want to, what I can do is just separate the x's and y's. All right, so I've underlined the x's. How many x's are there? Well, there are 2. So that's going to be the same as x times itself twice, so x squared, times y 1, 2, 3, 4 times, y to the power of 4. So that's how you do problems like that. All right, number 12. Multiply as indicated and express your answers in exponential form. All right, so first one, x to the power of 4 times x squared. Do they have the same base? Yes, so I can just add the powers. What's 4 plus 2? 6, x to the power of 6. All right, let's take a little bit more of a complicated one. Let's say we have number E. That was A. Letter E. E is x cubed times, let's see, y to the 7th times x to the power of 9 times y to the 5th. All right, so the first rule of exponents says that I can multiply the ones that have like bases and simply add their powers. So what are our 2 bases? Well, we got x's and y's. So let's start with the x's because it's best to do variables in alphabetical order. So x to the power of 3 plus 9. So x to the power of 12. Y to the power of 7 plus 5. Y to the power of 12. All right, x to the power of 12, y to the power of 12. There we go. Now a slightly harder one. Let us do, let's do h. So h is 4x to the power of 9 times 9x to the power of 4. All right, so do we have any like bases with powers? Yes. X's. So what I'm going to do is I'm going to multiply the 4 and the 9 separately, and then I'm going to multiply the x and the x separately. So what's 4 times 9? 36. And remember, the commutative property of multiplication says I can multiply any of these different things in any order. So I can do 4 times 9, x times x, in whatever order it'll all turn out the same. So I got my 4 times 9 is 36, and then when I'm multiplying x to the 9th times x to the 4th, that's 9 plus 4. 36x to the 13th. All right, time for number 13. Find x in each of the following equations. 10 to the power of 6 times 10 to the power of 2 equals 10 to the power of x. That's really very simple. If we wanted to, we could solve this in a kind of a complex way, but we don't need to. We can just say, all right, well, what is 10 to the power of 6 times 10 to the power of 2? That would be 10 to the power of 6 plus 2, which is 8. So in this situation, x equals 8. Because 10 to the power of 8 is the same as 10 to the power of 6 times 10 to the power of 2. Okay. Now, what about this one? This one's a little interesting. We'll go to C. So C is like this. Negative 5 cubed times negative 5 cubed equals negative 5 to the power of x. So what is x? Well, are these common bases? Yeah, they're the same. So add your exponents and you get x. So x equals the power here, which is 3 plus 3. Just out of curiosity, oops, sorry, 6. 3 plus 3 is not 3, 3 plus 3 is 6. There we go. So just out of curiosity, it's not asking you to solve what is negative 5 to the power of 6, but just for the heck of it, let's do that. So negative 5 to the power of 6 is the same as negative 5 times negative 5 times negative 5 times negative 5. That's 4 of them. We need 2 more. There we go. 1, 2, 3, 4, 5, 6. So if I'm multiplying this by itself 6 times, how many negative signs are there? There are 6. 1, 2, 3, 4, 5, 6. I didn't even need to, write this out to figure that out, because if it's raised to the power of 6, it times itself 6 times. It's an even number. And anytime you have negative numbers being multiplied by each other, remember that if it's an even number of negative factors, your answer is going to be positive. If it's an odd number of negative factors, then it's going to be negative. So is our answer negative or positive here? It's going to be positive. And so now we would just say, well, what's 5 times 5, which is 25, times another 5, which is 125, times another 5. And so you could just keep going with the powers of 5. You know what? I'll just go ahead and do that on my calculator. Five times 5 times 5 times 5 times 5 times 5. And that would be 15,625. But the point that I wanted to make out of all this was that when your exponent is positive, then even if you got a negative base, your answer is going to be positive, because that would give you an even number of negative numbers being multiplied by each other. So I just figured I'd throw that tidbit in. All right, do I need to do any more of number 13? Let me take a look. Okay. I'll do one last. F. Okay, F. Negative 4 squared times negative 4 to the power of x equals negative 4 the power of 10. All right, so if these are the same base, which they are, then we can add the exponents. And if we add 2 and x, we get 10, right? So then what is x? Well, 10 minus 2 is 8. So 2 plus 8 equals 10. X, once again, is the power of 8. All right, next problem. We're going to go to number 14. Okay, this is one that I'm not going to do in entirety, but they provide you a table of the powers of 4. And it looks like this. 4 to the power of 1 is 4. 4 to the power of 2, hopefully you know, is 16. 4 to the power of 3 is going to be 64. And 4 to the power of 4 is 256. And I think I'll stop there. So it says, use the table of powers of 4 at the right to find the following products without doing any multiplying. So what I'm going to do is I'm going to change the problem so I don't have to write a really long table. I'm going to say, what is 4 to the power of 2 times 4 to the power of 1? Or, you know what, I'll just say 2. Make the answer more predictable. All right, so what would that be? Well, 4 squared times 4 squared. Do I have the same base of 4 in both? Yes, I do. So that means I can add the exponents. So what is 2 plus 2? 4. So 4 to the power of 4. So can I solve this without doing any multiplying if I have this table? Yes, because I know that 4 to the power of 4 is 256. So that's all they're asking you to do with these types of problems, where they give you a table. You just basically figure out what your power is, and then look at the table and say, oh, that equals whatever it is. So pretty simple. Number 15. All right, find each of the following products, in other words, multiply. Express each answer in scientific notation. So number 1, we've got 3, that's a terrible looking 3, times 10 to the power of 4, times 2 times 10 to the power of 3. All right, so remember my strategy for solving these? We're going to take the things with the same base, add their exponents, and then everything else we just multiply. So 3 times 2, 6. 10 to the power of 4 times 10 to the power of 3 is going to be 10 to the power of 4 plus 3. And that's my answer. 6 times 10 to the power of 7. Now, always when you do these and you have to have a scientific notation answer, always look at your problem at the end and ask yourself, is it in scientific notation? Is this in scientific notation? Yes, I don't have to change anything. Let's take another one, though, where you would. I'll take F, the trickiest one. One thing I like about this book is it tends to do a good job of, actually I'm going to do 2 more, but I'll start with this one. It tends to do a good job of incrementally making the problems harder. So if you just do them in order, you're prepared for each successively harder problem. All right, so here, do I have more than 1 power of 10? I do not. And also, this one's not in scientific notation. But that's okay. It doesn't have to be at this stage, because what I could do is I could just say, all right, what's 0.5 times 12? Well, in other words, anytime you multiply something by 0.5 is the same as just dividing it by 2, saying what is it, what's half of 12? That's going to be 6. So I multiply this by this, and I get 6 times 10 to the power of 12. Because there's nothing to multiply this 10 to the power of 12 by. There's no other base of 10. Is this in scientific notation? Yes, it is. Now, what if I wanted to do this a different way? What if I wanted to convert this into scientific notation? Well, I could have. I could have done it like this. Move this over, and I get 5 times 10 to the power of 1. Because when I move this over to the right, to put it in scientific notation, I've multiplied by 10, and now I have to, I'm sorry, 10 to the power of negative 1. Then I would have to cancel that out by a negative power of 10, because that's the same as dividing. Remember I said last lesson that when you have a negative power of something, it's dividing by it. And then I can multiply this by 12 times 10 to the power of 12. And then 5 times 12 is 60. These are the same base. So what's 12 minus 1? That would be 11, 10 to the power of 11. Is 60 times 10 to the power of 11 the same as 6 times 10 to the power of 12? Yes, it is. But which one's in scientific notation? This one. So what I can do then is I would say, all right, to put this in scientific notation, I have to divide it by 10. And if I divide it by 10 over here, I got to raise my power to multiply by 10, cancel that out. So yeah, 2 different ways to come up with the same answer. Which one was better? I'd say this one. In fact, if this bottom explanation confused you, just pretend I didn't do it. Because at this stage, you're really okay just solving it the first way. All right, one last of this type of problem. I'm going to do, let's see. I think I'll do C. All right, so C is 6 times 10 to the power of 7 and 5 times 10 to the power of 2. All right, so first of all, what are our bases for the exponents? 10. So I can add those powers because they have the same base. So first of all, 6, times 5 is 30, right? Times 10, and what's 7 plus 2? That'll be to the power of 9. Is this in scientific notation? Not quite. To get it there, I have to move the decimal over to the left 1, which is the same as dividing by 10. So if I divide by 10 over here, I got to cancel that out by multiplying by 10 over here. In other words, raising the power of 10 by 1. So I end up with 3 times 10 to the power of 10. All right. Moving on, we are almost done. We're going to go to number 16. There are approximately 3 times 10 to the power of 7 cubic kilometers of ice on the Earth. That's a lot. 1 cubic kilometer is equal to 10 to the power of 9 cubic meters. I won't write that yet. How many cubic meters of ice are there on the Earth? And write this number in decimal form. So A, first of all, how many cubic meters of ice are there on the Earth? So we know that 1 cubic kilometer is equal to 10 to the power of 9 cubic meters. So how then do I figure out how many cubic meters there are? Well, think about this. We have 10 to the power of 7 cubic kilometers, right? And every one of those cubic kilometers is going to be 10 to the power of 9 cubic meters. So I could take this original number and multiply it by 10 to the power of 9, and I would be converting from the number of cubic kilometers I have to the number of cubic meters. So let's do that. 3 times 10 to the power of 7 times my conversion, 10 to the power of 9. Same bases, so I can add the exponents. 3 times 10 to the power of 7 plus 9, 16 cubic meters of ice on the Earth. That's a lot. All right, and then it says to write that number in decimal form. All right, well, that's going to take a while, but let's do it. Writing it in decimal form just means multiplying it out and then adding a decimal at the end if there isn't already one in the number. So 3 with how many zeros? 10 to the power of 16, so 16 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Add commas every 3. All right, so just out of curiosity, and then it's cubic meters, so I'll add a meters cubed. So let's see, that's going to be thousands, millions, billions, trillions, 30 quadrillion cubic meters of ice. That's a lot of cubic meters of ice. Finally, let's do number 17. All right, the fastest camera in the world, back then, when they wrote this book, is capable of taking 600 million pictures per second. That's kind of amazing. There are 3,600 seconds in an hour. Write each of these numbers in scientific notation. So our information again, 600 million pictures per second. So let's write 600 million. All right, so thousands, millions. So in scientific notation, that would be 6 times 10 to the power of 1, 2, 3, 4, 5, 6, 7, 8. And then the other number was there are 3,600 seconds in an hour. So in scientific notation, then that would be 3.6, because you put the first non-zero digit to the left of a decimal, times 10 to the power of, so if I had 3.6 and I moved the decimal over until it equaled this number, 3.6, 1, 2, 3, 3 places. All right, so that was A, writing those out in scientific notation. Now we're going to do B. Let's see how tough this is. If the camera could operate continuously at this rate, how many pictures could it take in an hour? Express your answer in scientific notation. All right, so we can actually do that much easier in scientific notation than if we weren't using scientific notation. So they're saying if you can do it this many pictures, 6 times 10 to the power of 8 per second, and there are this many seconds in an hour, 3.6 times 10 cubed, then how many of these per second can you do in an hour? So we're going to multiply this by this. 6 times 10 to the power of 8 times 3.6 times 10 cubed. We'll multiply this out. First of all, what is 6 times 3.6? I'll just do that over here. 6 times 6 is 36. 6 times 3 is 18, plus that 3 we carried, so that's 21, 216. Now I'm going to do the tens place. Actually, no, I don't need to, sorry. And so now we're going to move our decimal place over 1, because we had 1 decimal place in these factors. So that's going to be 21.6, which is, again, 6 times 3.6 times, now these have the same base, so we can add their powers. What's 8 plus 3? 11. 10 to the power of 11. Now am I done? Am I in scientific notation? Very nearly, but I got one problem. I can't have 21.6 because that's bigger than 10. For scientific notation, I need to have my first non-zero digit immediately to the left of my decimal. So, got to move my decimal over 1. And so I get 2.16 times 10 to the power of, it was 11, but look at this. I had to divide my number by 10 in order to make it scientific notation format. So I have to compensate for that by multiplying it by 10 over here. So instead of 10 to the power of 11, it's 10 to the power of 12. And you can check your work by saying, all right, does this number equal this one? Yes, it does, because 2.16 times 10 to the power of 12, in other words, with 12 zeros, or moving the decimal place over 12 times, would be the same as 21.6, where the decimal's already been moved over 1 times 10 to the power of 11. So there you have it. All right, well, hope this helped, and I'm going to turn out more videos of this type from this particular chapter, so stay tuned for those. Thank you very much. God bless.